Somewhere out there, at the very edge of what our telescopes can see, there are galaxies that shouldn't exist. Not because they're strange to look at, because of when they showed up. The James Webb Space Telescope has been staring into the deepest, oldest light in the universe, and it keeps finding galaxies that are too big, too bright, too formed, far earlier than any model said they could be. Structures that should have taken billions of years to build, already sitting there, fully grown, when the universe was barely out of its infancy. At first, scientists called it a puzzle, then a tension. Now a few of them are whispering something stranger. What if the problem isn't the galaxies? What if the problem is where we're standing to look at them? Because a small, serious group of physicists is asking a question that sounds like fiction and reads like a peer-reviewed paper. What if everything we can see, every star, every galaxy, this entire universe, is sitting inside a black hole? Stay with me. This gets stranger the deeper you go. Let's talk about what actually happened, because the real story is stranger than any headline could compress it into. When the James Webb Space Telescope launched in late 2021, astronomers had a rough idea of what they'd find when they pointed it at the earliest reaches of the universe. Based on decades of work building what's called the standard model of cosmology, the framework that describes how the universe expanded, cooled, and slowly assembled itself into stars and galaxies. The first galaxies should have been small, faint, barely formed, clumps of gas and young stars still figuring out how to become something. Instead, within months of Webb's first images going public, teams of astronomers started reporting something that didn't fit. Galaxy candidates from just a few 100 million years after the Big Bang, a sliver of cosmic time, practically the universe's infancy, that looked far too massive, far too structured, far too mature to exist yet. One of the researchers at the center of this, astronomer Ivo Labe and his colleagues, identified candidate galaxies so bright and so massive that, if confirmed, they would contain roughly as much stellar mass as our own Milky Way, but forming within the first 500 million years of the universe's 13.8 billion year history. For comparison, the Milky Way took billions of years to build up that kind of mass. These candidates seemed to be doing it almost instantly, cosmically speaking. At first, the reaction from most of the field was caution, not panic. Some of these early bright objects turned out, on closer inspection, to be something else entirely. For instance, actively feeding black holes, whose intense glow can mimic the light of a massive galaxy from a distance. That's a real and important part of this story. Not every impossible galaxy stayed impossible once scientists gathered more data. Peer review is slow on purpose, and some of the most dramatic early claims have since been narrowed down or reinterpreted. But even after accounting for that, even after the most obvious false alarms were filtered out, a real tension remained. Spectroscopically confirmed galaxies, meaning their distance and age were verified not just by color and brightness, but by breaking their light down and reading the actual physics inside it, kept showing up earlier, brighter, and more structured than to the standard model predicted was possible. Researchers now sometimes call these objects little red dots, a population of compact, surprisingly luminous sources from the universe's early centuries, whose true nature is still being debated in the literature. This isn't a fringe observation. It's been discussed in Nature, in the Astrophysical Journal, in conference halls full of cosmologists who spent their careers building the model, now being tested against it. Some researchers argue the fix is technical, that galaxies in the early universe simply converted gas into stars far more efficiently than expected, packing more light into less time than anyone assumed. Others think the resolution might involve revisiting assumptions about dark matter or about how the first generation of stars behaved. Both are live, serious possibilities, actively being worked through with new data as Webb keeps observing. And then there's the possibility that sits further out on the edge of the conversation. Not mainstream, not settled, but published, debated, and taken seriously enough that it keeps resurfacing every time a new too early, too big galaxy shows up in the data. What if part of the problem isn't only about how fast galaxies form? What if it's about the frame we're using to measure fast in the first place? Because standard cosmology assumes a particular kind of container, a universe born from a single expansion event, with a particular geometry, a particular relationship between space and time that determines how old something is allowed to look at a given distance. Change that container, even slightly, and the ages you calculate for these early galaxies change with it. Not because the galaxies changed, because the ruler you're using to measure them did. This is where things start to get genuinely strange, because one of the containers some physicists have proposed, seriously, mathematically, not casually, is one where our entire observable universe isn't expanding freely into empty space at all. It's expanding inside something, bounded by something. And the something some of them point to has the same basic mathematical signature as the inside of a black hole. I know how that sounds. Stay with me, because the physics behind it is more careful than the headline. The idea has a name, or rather a few different names, because more than one physicist has arrived at some version of it from a different direction. One of the clearest versions comes from physicist Nikodem Poplawski, who has spent years working on a modification of general relativity called Einstein-Cartan gravity. In the standard picture, when a massive star collapses, it crushes down into a singularity, a point of infinite density where the equations of physics simply stop making sense. Poplawski's work suggests something different happens if you include a property called torsion, a kind of twist built into the structure of space-time itself. Instead of collapsing into an infinite point, matter falling into a black hole reaches an enormous but finite density, then bounces, and on the other side of that bounce, in his framework, a new expanding region of space-time is born, a new universe from the perspective of anything inside it. In this picture, every black hole in our universe might be doing the same thing on the other side of its event horizon, quietly seeding a new universe we'll never observe. And by the same logic, our own universe could be the inside of a black hole that formed inside some other, larger universe we'll never observe either. That's a genuinely different idea from another black hole-related proposal you may have heard of, from physicist Lee Smolin, called cosmological natural selection. Smolin's version isn't about torsion or bounces specifically. It's a broader hypothesis that universes reproduce through black holes over vast timescales, with the physical constants of each daughter universe varying slightly from its parent, and universes that happen to produce more black holes effectively outcompeting others in a kind of cosmic evolution. It's worth being precise here. These are two distinct proposals from two different physicists built on different mechanisms, even though popular science writing sometimes blends them into one vague idea of the black hole universe. Neither of these is mainstream accepted cosmology. To be clear about where the field actually stands, the overwhelming majority of cosmologists still work within the standard expanding universe model, and for good reason. It explains an enormous range of observations with remarkable precision, from the cosmic microwave background to the abundance of light elements formed in the early universe. Black hole cosmology proposals remain minority positions, published and debated in serious journals, but far from settled, and far from replacing the standard picture. So why bring it up at all? Because of a strange, specific prediction these ideas make that ordinary cosmology doesn't. If our universe really did form from the collapse of something, inheriting some property, some residual spin, some preferred direction from whatever it came from, then galaxies across the universe shouldn't be oriented completely at random. There should be a subtle, detectable bias in which way they rotate. And in 2024, an astronomer named Lior Shamir, using Webb telescope data, published exactly that kind of finding. Looking at a sample of distant galaxies, Shamir reported an imbalance in rotation direction. More galaxies spinning one way than the other, at a level that shouldn't happen if orientations were purely random, the way standard cosmology generally assumes. It's a single study, not a consensus, and other researchers have pushed back on the methodology and the significance of the result. But it's exactly the kind of anomaly that keeps this conversation alive instead of letting it fade into pure speculation. I want to be honest about the shape of this evidence because that honesty matters more to me than the drama of the claim. Nobody has proof that we live inside a black hole. Nobody has proof that our universe is the child of some larger structure we'll never see the outside of. What exists is a small set of theoretical frameworks built by working physicists that happen to produce testable predictions, and a small contested set of observations that don't quite behave the way the mainstream model expects them to. That's not a confirmed discovery. That's the early, uncomfortable, unresolved stage where good science actually happens, long before anyone's sure which direction it's heading. What makes this particular thread worth pulling on isn't that it promises a tidy answer. It's that it connects two things that seemed, until recently, to belong to completely separate conversations. On one side, the ordinary physics of collapsing stars and event horizons, worked out over a century of careful mathematics. On the other, the impossible-looking galaxies Webb keeps finding at the edge of observable time. Nobody set out to link them. The link showed up on its own, in the data, in the equations, in the small, stubborn discrepancies that refuse to resolve themselves the easy way. There's another piece to this, and it comes from a slightly different angle. Not from someone trying to explain where black holes lead, but from someone trying to explain something that's been bothering cosmologists for years: dark energy. Physicist Enrique Gastanaga, working with colleagues, published research proposing something that sounds almost too simple. What if the accelerating expansion of our universe, the mysterious push that dark energy is supposed to explain, isn't actually being pushed by some exotic, unknown substance at all? What if it's simply what the inside of a black hole looks like, described using nothing more exotic than standard general relativity? The same physics Einstein wrote down over a century ago. In their framework, a black hole massive enough, collapsing under the right conditions, wouldn't necessarily crush everything down to a singularity. It could instead settle into an expanding interior. And an observer inside that interior, unable to see past its own horizon, would experience that expansion exactly the way we experience the expansion of our universe, including potentially the acceleration we currently attribute to dark energy. I want to slow down on that for a second, because it's easy to let the phrase "we live inside a black hole" turn into pure spectacle and lose the actual elegance of what's being proposed. Dark energy, as it currently stands in mainstream cosmology, is one of the strangest unexplained ingredients in all of physics. It makes up roughly 70% of the total energy content of the universe by current estimates, and nobody knows what it actually is. We gave it a name because we needed one for the math to work, not because we understood the thing itself. Any framework that could explain that same acceleration using only physics we already trust, without inventing a new substance, is going to get serious attention from serious people. That's not fringe thinking. That's just physicists doing what physicists are supposed to do, reaching for the simplest explanation that fits the data wherever it leads. Now, the honest counterpoint, because this deserves one. Most cosmologists working on dark energy remain unconvinced by black hole cosmology models for reasons that are entirely reasonable. The standard model, despite its odd, unexplained ingredients, has survived decades of increasingly precise tests. measurements of the cosmic microwave background, the large-scale structure of galaxy clusters, the rate of expansion measured multiple independent ways. Black hole cosmology proposals are newer, less tested, and still need to show they can match that same level of precision across every observation, not just the specific tension that they were built to explain. Explaining one anomaly elegantly doesn't automatically mean you've explained the whole universe correctly. But here's what keeps this from being dismissed outright. Anomalies in physics have a track record. They're often treated at first the way a slightly odd shadow gets treated. Background noise, an error in the instrument, something to be quietly corrected later. And then occasionally, decades pass, and it turns out the shadow was the first sign of something enormous nobody had named yet. The precession of Mercury's orbit looked like a minor discrepancy for over half a century before it became one of the pieces of evidence that helped confirm general relativity itself. Nobody is claiming the just-T galaxies or the rotation asymmetry or the black hole cosmology models are that scale of revolution. It's far too early to say that with any honesty, but the pattern is familiar enough that physicists working in this space have learned not to dismiss small, stubborn discrepancies just because they're inconvenient. Sometimes inconvenient is exactly what a real discovery looks like, right before anyone understands what they're looking at. And there's something almost dizzying about holding these two pictures side by side. In one, you're standing on a small rocky planet, orbiting an ordinary star, in one arm of an ordinary spiral galaxy, inside a universe that simply exists, expanding outward from an initial event, following rules that were fixed the moment it began. In the other, that same planet, that same star, that same galaxy, all of it, exists somewhere inside the collapsed remains of something else. A structure with a boundary you'll never reach and outside you'll never see, formed by a process older and larger than the universe you're currently capable of measuring. Both pictures use real mathematics. Both are being worked out by people with the training to know the difference between an interesting idea and a testable one. And right now, nobody, not the physicists proposing it, not the ones pushing back on it, actually knows for certain which picture is closer to true. Let's sit with the strangest implication for a moment, because it's easy to rush past it. If any version of this is even partially right, then the black hole you picture, the kind astronomers photograph, glowing rings of matter spiraling into darkness, isn't an ending. It's a birth canal. Every collapsing star, every galactic core swallowing its neighbors, every supermassive black hole quietly growing at the center of a galaxy could be the opening act of a universe none of us will ever see formed. And by that same logic, somewhere unimaginably far outside whatever boundary contains us, some other collapsing star in some other universe might have been the opening act of everything you've ever known. That reframes an entire category of objects we've spent decades learning to fear. Black holes get treated, culturally, as cosmic destroyers. Places where physics breaks, where matter goes to be erased. And in a very real sense, from the outside, that's true. Nothing that crosses an event horizon comes back the way it went in. But if researchers like Poplawski and Gastanaga are onto something, erased might be the wrong word entirely. It might be closer to transformed. Not an ending, a threshold. There's a related idea worth mentioning here because it connects to something physicists have wrestled with for decades and rarely explain well outside academic papers. The fine-tuning problem. Our universe's physical constants, the strength of gravity, the mass of an electron, the rate of cosmic expansion, sit within an extraordinarily narrow range that allows atoms, stars, chemistry, and eventually life to exist at all. Nudge almost any of those numbers even slightly, and you get a universe with no stars, no chemistry, Nothing capable of asking why any of this happened. For a long time, that narrow range has puzzled physicists, because there's no obvious reason the numbers had to land exactly where they did. Smolin's cosmological natural selection, the framework we mentioned earlier, was actually built to address exactly that puzzle. If universes really do reproduce through black holes, and if the physical constants of each new universe vary slightly from its parent, then over immense timescales, something like evolution could take over. Universes that happen to produce more black holes would, in effect, produce more offspring universes carrying similar constants. Over countless generations, the constants that maximize black hole production could become the norm. And because the same conditions that favor black hole formation, like long-lived stars fusing heavy elements, also happen to favor complex chemistry, it's not a coincidence that a universe optimized for making black holes might also happen to be a universe capable of making us. I want to be careful here, because this is exactly the kind of idea that's beautiful enough to want to believe before you've earned the right to. It's elegant. It solves multiple problems at once, at least on paper. But elegance isn't evidence, and Smolin himself has been transparent that the hypothesis remains difficult to test directly, since we can't observe universes other than our own, and can't watch black holes actually give birth to anything from where we're standing. It's a real, published, seriously argued idea, and it's also, by its own author's admission, unproven. What I keep coming back to isn't any single piece of this. It's the shape of the whole conversation. A century ago, the idea that our universe had a beginning at all was controversial, resisted even by some of the physicists who'd later be credited with proving it. 50 years ago, black holes themselves were treated by many serious scientists as a mathematical curiosity, not something that could possibly exist in the real universe. Both of those ideas moved from fringe to foundational, not because someone found irrefutable proof overnight, but because the evidence kept accumulating, quietly, stubbornly, until dismissing it took more effort than accepting it. Nobody knows yet which category this idea falls into. Maybe it fades, the way most edge-of-the-field proposals eventually do. Maybe it's the next thing that moves from strange to standard. The honest answer, right now, today, is that we simply don't know. And maybe that uncertainty is worth sitting inside for a moment, instead of rushing past it toward a conclusion. We're used to science handing us finished answers, a fact you can repeat at dinner, a number you can quote with confidence. This isn't that. This is the messier, more honest version of how discovery actually works. Somewhere in the gap between a stubborn anomaly and a theory solid enough to teach in classrooms. You're watching that gap in real time, which is rarer than it sounds. So how would anyone actually find out? Because that's the part that separates a fascinating idea from an untestable one, and it matters to know which side of that line we're standing on. The good news is that these aren't the kind of proposals that live purely in philosophy. They make predictions, and predictions can be checked. The rotation asymmetry Lior Shamir reported in 2024 is exactly that kind of check. A specific, falsifiable claim that more galaxies spin one direction than the other, at a level random chance shouldn't produce. As Webb keeps gathering data, and as other telescopes come online, that result will either strengthen with a larger sample or wash out into statistical noise, the way plenty of promising anomalies eventually do. Either outcome tells us something real. The James Webb Space Telescope isn't finished either. It's still cataloging galaxies from the universe's first billion years, still spectroscopically confirming which of the too early, too massive candidates hold up under closer inspection and which turn out to be something more ordinary. Every confirmed galaxy adds a data point to a picture that's still being drawn. And upcoming instruments, like the Nancy Grace Roman Space Telescope, are being built specifically to survey far larger patches of sky than Webb can manage alone, which means far more of these early galaxies to check the pattern against. There's also a subtler kind of evidence physicists are watching for, tied to the torsion at the heart of Poplawski's framework. If space itself really does carry that kind of twist at extreme densities, it could in principle leave faint signatures in gravitational waves. The ripples in space-time that detectors like LIGO have been catching since 2015, mostly from colliding black holes and neutron stars. Nobody has found that signature yet, but the instruments keep getting more sensitive, and the catalog of detected collisions keeps growing, which means the window for either finding it or ruling it out keeps getting narrower. None of this resolves anytime soon. That's not evasiveness on my part. It's genuinely how this stage of science works. The universe doesn't owe us an answer on our timeline, and the physicists chasing this down know that better than anyone. What they're doing, patiently, methodically, paper by paper, telescope by telescope, is narrowing the space of what's still possible. That's slower than a headline wants it to be. It's also the only way any of this has ever actually gotten settled. It's worth remembering how long that narrowing usually takes, even for ideas that turned out to be true. Gravitational waves were predicted by Einstein in 1916, almost as an afterthought in the mathematics of general relativity. It took a full century, until 2015, before an instrument sensitive enough to actually detect one was built and switched on. 100 years between prediction and proof, with generations of physicists working, publishing, arguing, never certain the confirmation would come in their lifetimes. Some died without seeing it. The ones who came after inherited the question and kept going anyway. That's the part of science that rarely makes it into the popular version of the story. Not the breakthrough itself, but the long, uncertain stretch of people building towards something they can't yet prove, because the alternative is simply not looking. Whatever the true answer turns out to be here, torsion bounce, black hole interior, something nobody's proposed yet, or the standard model quietly resolving its own tensions, someone alive right now is doing the slow, unglamorous work of finding out. And you're getting to watch that work happen in something close to real time, which is a genuinely unusual position for a member of the public. If you've made it this far with me, into torsion and singularities and galaxies spinning the wrong way, I want to say something honest. This is exactly the kind of story I built this channel for. Not the easy version of the universe, the one with tidy answers and clean endings, but the real one. Strange, unfinished, argued over by people who've spent their whole lives trying to get a little closer to the truth. If that's the kind of thing you want more of, subscribing genuinely helps, because we put out something like this almost every single day, and it means these stories reach more people who'd actually want to hear them. And if you've got a question sitting in the back of your mind right now, something this raised that you want answered properly, drop it in the comments. I read everyone, and some of the best videos on this channel started exactly that way. Because there's still one more layer to this. The strangest one. What it would actually mean for you, for me, for everyone who's ever looked up at the night sky and felt small, if it turned out we really were living inside something else's collapse. So let's actually go there. What would it mean if it were true? Not in the equations, in your actual life. On an ordinary Tuesday, making coffee, half listening to the news, completely unaware that the ground beneath your feet, the sky above your head, the stars you can just barely make out past the light pollution, all of it exists inside the collapsed remains of something else. The first thing worth saying is what wouldn't change. Gravity would still pull you toward the Earth. Sunlight would still warm your skin. your heart would still beat the same way it does right now, whether the universe around it is a freestanding expanse or the interior of some unimaginably vast, collapsed structure. Physics inside of the boundary doesn't suddenly stop working because of what the boundary is. That's actually one of the more unsettling parts of this whole idea. Not that everything would look different, but that almost nothing would. You'd never feel the difference. There'd be no sensation of being inside anything. The same way you don't feel the Earth hurtling it through space at over 100,000 kilometers an hour right now. Containment at this scale isn't something a nervous system evolved to detect. What would change is something quieter and harder to point to. It's the shift from thinking of the universe as the biggest possible container, the outermost thing, the frame nothing else sits inside, to thinking of it as one structure among an unknown number of others, nested inside something we have no way of ever observing. Not smaller in any way that matters to your actual day, but differently shaped in the deep architecture of what everything even means. I think about how many times across history humans have had to make exactly that kind of adjustment. There was a time we believed Earth sat at the exact unmoving center of all creation, with the sun and stars built around us. That got corrected and it stung, genuinely, for the people who had to let it go. Then we believed our sun was the center of everything, until we learned it was one ordinary star among hundreds of billions in a single galaxy. Then we learned that galaxy was one among hundreds of billions more, scattered across a universe so large that light from its most distant visible galaxies has been traveling toward us for over 13 billion years just to arrive. Each of those corrections felt, at the time, like a demotion, like the universe was quietly telling us we mattered less than we'd assumed. And each time, eventually, the demotion turned into something closer to wonder, once people sat with it long enough. Not because the facts got kinder, because we got better at holding the facts without needing them to flatter us. This might be the next correction in that same long line. Not you are smaller than you thought, exactly, but the container you thought was final was never final. And if history is any guide, that reframing won't feel comfortable at first. It might not feel comfortable for a generation, or several. The way heliocentrism took uncomfortably long to fully settle into public understanding, even after the mathematics was solid. But I don't think discomfort is actually the right response to reach for. Because here's what strikes me most, sitting with this idea for as long as I have while putting this video together. If we really are living inside the aftermath of some vast collapse, born from a structure with no outside will ever reach, that doesn't make anything about your life smaller. It makes the event that produced you almost unbearably strange and specific. Some star, somewhere, in some universe none of us will ever glimpse, had to collapse in exactly the right way, under exactly the right conditions, to produce a universe with the physics needed for chemistry, for planets, for you to be sitting here right now, hearing about it. That's not a smaller story. That's a stranger, more improbable one. And improbable has always been where the best stories live. There's one more thread worth pulling before we close this out, because it changes how the whole idea sits in your mind. If universes really can form this way, nested inside collapsing structures, generation after generation, then the process didn't necessarily start with us, and it almost certainly won't end with us either. Somewhere inside the black holes scattered across our own galaxy, across every other galaxy Webb has ever photographed, something might already be happening on the other side of their horizons that no equation we currently possess can fully describe. Not a metaphor, a physical process playing out right now, completely inaccessible, completely real. We'd never see it. We'd never need to. It would simply be happening the way our own beginning simply happened, somewhere upstream of anything we're capable of observing, Here's where this actually leaves us. Galaxies that shouldn't exist yet, sitting patiently in Webb's deepest images, staring at the standard model to explain them. A handful of physicists working the math from strange new angles. Torsion instead of singularities, black hole interiors instead of dark energy, because the old explanations, however trusted, still have gaps nobody's fully closed. A rotation asymmetry that may be nothing, or maybe the first real hint that our universe remembers where it came from. None of it is proof. I want to say that clearly, one more time, because I'd rather you walk away from this with an honest question than a false certainty. Nobody has shown that we live inside a black hole. What's actually been shown is smaller and in some ways more interesting. That the universe keeps producing observations the simplest story can't fully explain, and that some of the sharpest minds working on it are willing to follow that discomfort wherever it leads, even toward an idea this strange. Maybe in 10 years, this gets resolved quietly, folded into a slightly adjusted version of the standard model, and this whole conversation becomes a footnote. Or maybe it doesn't. Maybe it's the beginning of the next real shift in how we understand where we are and what we're standing inside of. Physics has a long history of both outcomes, and no reliable way to tell in advance which one you're watching unfold. Either way, you were here for the part that mattered most, the uncertain middle, before anyone knew how it would end. That's rarer than a finished answer, and honestly, a little more honest too. I'll leave you with the same question the physicists are still sitting with. Not whether we're inside a black hole. Something simpler, and somehow harder. If the boundary of everything you've ever known turned out not to be the edge after all, just a threshold, would that change how you looked at the sky tonight? I'll see you in the next one.